So we're going to talk today about multiplying polynomials. We've been talking, in general, we've been talking about exponents and polynomials for this whole unit, and we're going to keep going with polynomials, but today we're going to talk about multiplying them. So the reason that we talked about integer exponent rules, so with positive and negative exponents, is because we're going to use that when we talk about multiplying exponents. So I was talking with Brendan when we were doing the rewind, and he asked, when do you add the exponents together, or when do your exponents increase? We talked about how you have to do that when you're multiplying exponents, but when you're adding them, you just combine the like terms, but the exponents stay the same, right? So that does get a little bit confusing because it seems like if you're adding them together, your exponents should get bigger. But remember, exponents getting bigger only happens when you're multiplying a number times a number because you're getting more of those m's. So for example, in number 1, if you did 3m to the third times 8m to the third, then your exponents would increase, but not when you're adding. So when you're adding, we're just looking for common like terms. Everybody did really well on 1, 2, and 3, but what happened with number 8 to a lot of people? Forgot to distribute that negative, which I said is the one thing that you guys make mistakes on all the time, just because you're trying to work too quickly or forget that you have to do it. So just be extra careful when it's a subtraction problem, because this negative sign, this minus sign it acts like a negative and it distributes to everything in the parentheses, which is why we put those parentheses there. Okay? So that's the whole point of the parentheses, as a reminder for yourself to distribute that sign from the outside. All right, so take a look at this multiplication. So we're going to do multiplication of monomials here. So when we multiply monomials, I want you guys to remember the properties for multiplying exponents. So before we even start, if I were to multiply x to the 8th times x to the 3rd, what would I get? X to the 11th. Why? What? 8 plus 3 gives you 11, right? So when you have an exponent with the same base and you're multiplying, what do you do with your exponents? Add them together. Because again, how many x's is this? 8, and how many is this? 3. So if we're just putting them together, it ends up being 11. So when we multiply with monomials, you have something like this, where you've got 5x to the second and 4x to the third. The good news is we don't have to have like terms. So I say often that monomial rules and polynomial rules are very similar to fractions. You don't need common denominators when you're multiplying. You do when you're adding, you don't when you're multiplying. So just like with monomials and polynomials, when we're adding and subtracting, we need like terms. We don't need like terms when we're multiplying. So does anyone have a guess on how you would do this? Does anyone have a guess on how you would do this? Emily, what do you think? Okay, so we're going to multiply the coefficients, which gives you what? 20. And then what? Okay, so that will give you what? X to the 5th. And that's exactly right. So you multiply the coefficients, and then you combine your exponents because you've got the same base. Brendan? Well, the other problems were addition and subtraction, so no. So again, addition and subtraction, you have to have like terms. Multiplication, you do not. Multiplication, you're basically multiplying your coefficients, and then you're looking at it, because really, these are all a long string of multiplication problems. So you can do 5 times 4, and then x squared times x to the 3rd, which ends up giving you x to the 5th. All right, what if you had something like this? What do you think this would give you? I don't see a coefficient in front of my second one, so what can I do? Imaginary 1 in there. So Guillermo, if I put an imaginary 1 in here, then in my answer, what's the coefficient of my answer going to be? 8. Why is it still 8, Guillermo? 8 times 1 still gives you 8. Good. What about the variables in there? What do you think the variables in my answer should be? What? So it would be y to the 5th and then x to the, good. All right, So 8xy, x is to the third, y is to the fifth. How come y is to the fifth now? Yeah, because you're multiplying those together. And then x to the third stays x to the third because there's no other x's. All right, I put it in that order because it's in alphabetical order. It doesn't really matter since multiplication is commutative. All right, if you'd rather have that bigger first, that's fine. Now, there's no signs in between here, but it's a monomial. What's the degree of this monomial? What's the degree of this monomial? What? No, it's not a trinomial. A trinomial would have 3 separate terms. 8. Why is it 8? Okay, so when you're talking about the degree of a monomial, you add them all together. So it's 3 plus 5. It's only a trinomial, or you only pick the biggest one if it had something like this. All right, this would be a trinomial. Again, you need a plus and minus sign to separate into different terms. Okay, so take a look at B. Take a look at B. What do you think B would be? Diego, what do you think? Y 7? Good. Where'd you get that from? Okay, add your exponents of your similar bases. So add the x's together. This one's a 1, this one is a 1. And then you've got y to the second, y to the fifth, so that becomes y to the seventh. Where did the negative 12 come from? Yeah, negative 3 times 4. Negative 3 times 4. All right, so when you multiply those, when you multiply 2 monomials together, your answer should still be a monomial. What's going to happen in this one? What do you think? Brendan, what do you think here? What are my variables going to be? A, B, and C? I'm still going to have A, B, C. All right, what's the exponent of the A? 5. Why is it 5? Because there's a 3 and a 2 there. All right, what about the exponent of the B? 3. Why is it 3? There's 1 here and 2 here, so that's 3. Okay? And then what about my C's? Just 2, because there's only C's right here. All right, so it'd be C to the second. Now you just have to figure out what the number in front is. What's the number in front of here? What's 1/2 times 1? 1/2. And then 1/2 times 6. What's half of 6? 3. So my coefficient would be 3. All right, again, if you're doing it on a calculator, you can change 1/2 to what? 0.5, and that will work too. All right, so same thing. So again, you figure out what your exponents are by adding together when they're similar bases. Do not forget that when there's no number, it's got to be a 1. All right, and then to get your coefficient in front, just multiply all of your coefficients. So if you want to use a calculator for that, by all means do. All right, what if I had this? What's going on here? Yeah, but what is this right now? Brendan? It is an expression. Emily? It's a trinomial times a monomial. It's a monomial times a trinomial. So how many multiplication problems am I doing here? 3, because I have to do 5 times this first one, 5 times this second one, and 5 times the third one. So I should end up with a trinomial. So what's 5 times 2? 10. So this should be 10 what? X2 plus what? 5x plus 20. Perfect. Okay? So I just distribute that monomial to everything inside the parentheses. All right, what about this green one? What about this green one here? What am I distributing? The 3a to everything. Okay, so if I distribute the 3a to this, what do I get? 3a, 3. Why? Because this has an invisible 1 right here. So if I combine that with this, I end up with a to the 3rd power. What about this one? 6a2. Good, 6a2, because there's an a here and an a here. So now there's 2 a's. Guys, make sure you're writing these down. All right, and the last one. 18a. Good. 18 with just the 1a. All right, who can come up and do B or C? Oh my gosh, what is happening? All right, B or C? I think it's because it's not lined up. No. Still no, but all right. There we go. All right, who can come up and do B? Ollie? Perfect. Great job. Okay, so the first thing she did was multiply 2 times 3, and she got 6. It's an x3 because we've got 2 here and 1x here, so it's x3. And there's still a y right here. And then last, it's minus 2 because 2 times negative y gives you negative 2. X squared came from here. And then there's 2 y's because there's a y there already. All right? And then what about C? Okay, come on up. I agree with everything except one number. Why should 6 be 8?
4 times 2.
Good, turn it into an 8. Good, perfect. That's a perfect 8. It looks just like an 8. All right, good. So 4a to the 3b plus 8ab squared. Okay, the biggest thing I would say is just make sure that if there's a letter, a variable out here, that even if it's not in your monomial in here, it gets into the answer because you've got to multiply that whole thing. Okay, go do these 6. All right, so when you're working on these, just make sure that if there's a variable on the outside, that carries over onto the inside. So for example, with this one is where I saw a ton of mistakes. So if you're doing this, I agree that it's 10, but don't forget you're multiplying a times a, so that would be a squared. And then over here, that's going to give you 100, but you've still got an a and you've got a b, so then it's ab. All right, so when you're multiplying monomials, you're distributing, just be careful with your variables. Okay, so what would you do then if you had to multiply these? First of all, what are we multiplying there?
X plus 2.
Yeah, what's x plus 2 called? It is an expression. Specifically what? Think back to naming polynomials. We just did it last week.
Oh, x plus 2 is called a binomial.
A binomial. So we're multiplying a binomial times a binomial. So we're doing a binomial times a binomial. How do you think we do that? What do you think?
I think first you
Well, you can't really work inside the parentheses because you can't do anything with x plus 2. There's nothing you can simplify there. So what do you think we can do? What do you think, Diego? Okay, so essentially we still use the distributive property. We're just using it twice. So we distribute the x to everything in the parentheses over here. And then we distribute the 2 to everything in the parentheses over here. So we basically end up doing 4 multiplication problems because we do the x times everything in the parentheses and the 2 times everything in the parentheses. So when you start it, the first thing you do is x times x, which is x squared. And then you do x times negative 5, which is what? 5x, good. And then you do 2 times x, which is plus 2x. And then you do 2 times negative 5, which is negative 10. And then what do you think the last thing you should do is? See if you can simplify it. See if you can combine like terms. Typically, the 2 in the middle are going to combine. Okay? So we've got a negative 5 and a plus 2, which gives us what? Negative 3x. This x squared doesn't simplify, and this negative 10 doesn't simplify. So our final answer ends up being a trinomial. All right, so typically, this isn't 100% of the time, but most of the time, a binomial times a binomial is a trinomial. So I hope that everybody wrote that down. All right, remember you should be taking notes all the time. If I write it down, you should write it down. Okay, so when you're multiplying binomials times binomials, we distribute. How many of you guys have heard the term FOIL before? Not many of you? All right, Mr. Vrandrick hates this term, so if you have him for Algebra 2, don't tell him I taught you this. But FOIL is just an acronym for a way to remember how to multiply binomials. So what does an acronym mean? Yeah, it stands for something. So FOIL stands for first, outside, inside, last. So you multiply your 2 first numbers, then you multiply your outside numbers, then your inside numbers, and then the last numbers. So all that means is a way to remind yourself that you have to do 4 multiplication problems. All right, essentially what you're doing is just distributing the same thing twice and then the next thing twice. And this distribution works no matter how big the problem is. All right, you could have a 6-term polynomial times a 6-term polynomial and still do it. It would just be 12 different, a lot of different, well, maybe 36 multiplication problems. Okay, I won't ever give you ones that big. All right, so when you're multiplying them, another way to organize it, especially as they get larger, is called the box method. How many of you guys in biology have seen Punnett squares? When you're doing like genetics, yeah, so you have like b and little b, big B, little b. And so when you do a Punnett square, what are you doing? Like again, let's say you have big B, little b, big B, little b. What would this one be? What kind of B's? 2 big B's. Why? Because it's these 2 that meet right there, right? So what would this one be? Big B, little b. This one would be, yeah, or it does, I guess maybe the order matters, maybe it doesn't. Okay, and then this one is little b, little b. So this one should be little big. Okay, all right, in math, it doesn't matter. So this Punnett square idea is the same thing as the box method. So I like the box method because it's typically something that you're already familiar with since you've done these in biology. I love the box method for a way of organizing. So essentially what the box method does is it takes your problem and puts it into each of the boxes. So this right here has 2 terms, so it's called a binomial. And this one has, so it's called a trinomial. So does anybody know where the binomial and the trinomial goes on this box?
Try is up there.
Try is up there, bi is on the bottom. Okay, so this would be 5x. This would be what? 3? What would this be? 2x to the second. This would be 10x. And this would be negative 6. Good. How come I only put the sign with that one? All the rest of them were positive, so the signs don't really matter that much. If it's a negative, you've got to put it. So then this box right here, what math problem am I doing to fill in this box? 5x times, which is going to give me what? 10x to the third. Very good. 10x to the third, because we've got a 1 here and a 2 there, so it gives us to the third. Brendan?
Do you think we should just start writing the ones next to it?
If it helps you, yeah. Do you want me to start on the board? Yeah? Okay, so then we put it here. All right, I think that's a good idea, so then you don't forget about it.
Yeah.
Okay, what about this box? 50x squared, because you're multiplying the 10 and the 5. Is everybody seeing which terms we should be multiplying for each of the boxes? Okay, all right, so then this box would be the negative 6 and the 5x to the 1, so what would that give us? Good. What about this box? This box? And this box? Okay, negative 18. 6 times 3 is 18, and it's a negative 6, so it's negative. Now, this is almost your answer, all right? But you've got to write it out in a way that makes sense. So we want to write it in one line, but before we do that, we want to combine like terms. The other reason I really like the box method is because if you set up your box right, usually your like terms will be on a diagonal. So you can see where your like terms are, because typically the diagonals are like each other, okay? So that's all we have to combine. So our first term is still 10x to the third. Our second term, we're going to combine the x squareds, which gives us what? 56x squared. And then here we're going to combine 30x and negative 30x. What happens there? That's gone. So do I write anything? No, it's gone. You could write plus 0. I wouldn't. Okay? And then last but not least, it would be negative 18. So that's it. So you have two options. You can either distribute, which especially for the shorter ones, like we did right here, is not that big of a challenge to just keep track of your arrows. But I'll tell you right now, if you're doing the distributive property here, you're going to end up with a lot of arrows. And so I think the box method is just a more organized way to do it, especially if you're the type of person who tries to do things mentally and works too quickly. Not that any of you guys would do that, but if you are that type of person, the box method can help slow you down, okay? And sometimes being slow is a little bit better. Now, I'm not always going to give you the box, so sometimes you're going to have to draw it yourself. And you could do it. Do you think it matters that the 2 were here and the 3 were this way, or do you think you could do it either way? It doesn't really matter. For some reason, I always put my longer one on the top. It doesn't really matter. It's just that I get in the habit of doing that. Yeah, so if this were like 5 terms, this box would be 5 terms. I mean, there would be 5 boxes. If this were 4, then you'd have 4 boxes going down. Again, this is probably the longest that you'll see. All right? But the number of terms tells you how many boxes there should be. Okay, and like I said before, typically you're going to have like terms on diagonals. So if you're looking for like terms, look diagonally from each other. Okay, so let's try this one. Do we want to just distribute or use the box method? Box method? Okay, so how big is this box going to be? 4, so it's only going to be 2 by 2. So I'm going to draw a box, 2 by 2. That's a really bad box, but it doesn't really matter. What goes up here? Negative b, and we'll put negative b to the 1. What goes down here? A squared, negative 2b to the 1. Okay, now, what's this box going to give me? 3a4. What's this box going to give me? Negative a2 b1. What's this box going to give me? 6 a2 b1. And then here? Positive 2. Why is it a positive 2? Negative gives you a positive. All right, and then b to the second. Good. Okay, Somebody said down here, negative 6b1a2. Is that wrong? No. But if you write it that way, you might miss the fact that these are what? Like terms. So if you write this one with the b first and this one with the a first, you might miss the fact that they're like terms. But again, these two are what? Diagonal. So that's where you always want to check for your like terms. Yes, these are like terms. So when I write my answer, I'm going to combine those two. This one has no like terms, so my first term is just 3a to the 4th. What does this give me? No, because I'm adding.
For that one there, isn't there an invisible one in front of negative?
Right here? Yep.
So isn't it negative 3?
Here? Or here? This would be negative 7. A2, B1. Because negative 6 and negative 1, when the signs are the same, you add them and always keep the sign of the bigger number. The bigger number is 6. So it's a negative 7. And then the last one would be plus 2b squared. All right, so once they're in the box, the exponents don't change. Once they're inside the box, you've got your box all done, the exponents stay the same. All right, so if this is a2b1, then this should be a2b1. The only thing that's going to change once you've got your box filled out is the coefficients. Okay. Can I get somebody to come do this one? Can I get somebody to come label it? Ash? Good, yes. Now that you're up here, go ahead. Good, perfect. X3. Good. Good. Perfect. All right, that's perfect. So you got, and did you guys notice that Ash went straight up and down, whereas I've been going across? Does it matter? No, whatever works out better for you. And then the very last thing is combine your like terms. Does this one have any like terms? No, so it's x to the 3. Then these two combine, which gives you 2 minus 5 would be negative 3x squared. Again, your exponents don't change. These are like terms. Ash put the one here. She didn't put it here, but those are like terms. What's negative 10 plus 4? Negative 6x to the 1. And then last but not least, plus 8, because that doesn't have any like terms. Okay, so you multiplied a binomial times a trinomial. What did you end up with? A polynomial with 4 terms. And it goes to the 3rd degree, so what kind is that? Remember, you got to memorize those words. Goes to the 3rd degree. Cubic. It's a cubic polynomial. Okay, for your exit tickets today, I'm going to actually have you guys do them on the board. So just do these 4 at your boards now.